For this second videotape, we've again come to the Department of Chemistry in the University of Manchester. One of the big differences in organic chemistry as it is carried on today, compared with a few years ago, is the scale of operations. I have here Robert Robinson's original paper where he announced his annulation reaction, a new general method for the synthesis of substituted cyclohexenones. And if we turn to the experimental section, we find that he began with methoxyphenyl propionic acid, 187 grams, and he dissolved that in absolute alcohol, 491 cc's, and so on. And then when he gets to the end, he's perhaps a bit disappointed to say the yield was diminished when the operation was conducted on a larger scale. Compare that with the synthesis of trichodermin, which I discussed towards the end of the course. Here the authors, towards the end of the start with 16.4 milligrams of their material, and they isolate 4 milligrams of product, which they then go on to recrystallize a second time. An obvious way of reducing the scale is to reduce the size of the apparatus, and miniature apparatus of this type, called B10, is available just for this. A number of pieces are displayed here, but the best idea of the scale can be seen by comparing the normal distillation apparatus with its B10 equivalent. When it comes to recrystallization, again, we can do things on a small scale. The 5mm filter paper, cut with a cork borer from a pad of filter papers, placed in a Hirsch funnel, will hold up a lot less of a recrystallizing solution than a fluted filter paper. It can be filtered under slight suction in this miniature Buchner apparatus. Alternatively, our hot solution can be filtered under suction in this Buchner apparatus with a loose bottom. And the solution allowed to crystallize in this small flask. When we need to obtain a small amount of solid for analysis, we can't risk contaminating our sample with filter paper hairs, and so all glass apparatus must be used. If we use one of these cone-shaped tubes, we can drain off the mother liquor using a dropper pipette. By pressing the square end of the pipette hard against the bottom of the flask, the mother liquor is withdrawn, leaving the crystals behind. The crystals can now be washed and the process repeated. And if necessary, a further recrystallization can be carried out in the same tube. For slightly larger quantities of solid, this glass nail, the Willstätter nail, can be used. It fits snugly inside this glass filter funnel, and we can use a sidearm tube in which the cone tube inside rests on cotton wool. The slurry of crystals and mother liquor is transferred with a dropper pipette and the solid is trapped in the space between the filter funnel and the nail head. When it comes to distillation of small quantities of liquid, one of the problems is that liquid is held up at each of the joints in the conventional quick-fit apparatus. In the diagram here, ingeniously, the joints have been avoided, and as a result, we can carry out distillation from this flask and collect several fractions by rotating this base in this all-glass apparatus. If we have even smaller quantities of liquid, we may need to use bulb-to-bulb distillation. Our impure liquid is placed in this bulb. Suction is applied at this end, and then this bulb is heated and this one cooled, with the result that liquid distills over from here and is in a purer form in this second bulb. Here is one in which that process has been carried out. There's even a commercial apparatus for doing this job called the Kugelrohr. Our impure liquid is placed in this flask, which is then inserted into the furnace. Suction is applied here, and liquid distills into this second bulb. We can carry out a further distillation, if we require, by moving this second bulb into the furnace and redistilling into this third bulb. Another major change in synthetic organic chemistry over the last 30 years is the development of more and more specific reagents. Unfortunately, many of these are very sensitive to air and moisture in the atmosphere, like the ones I have here. Fortunately, it is only the reagents and some intermediates that show this sensitivity. Normally, the products of the reaction can be worked up in the usual way. There are two approaches when we want to use these sensitive reagents in our reactions. One is to limit the exposure of the reagent to the atmosphere as much as possible, and the other is to create an artificial atmosphere in which to carry out our reaction. If we look at the diagrams, we see here two sets of apparatus when we can carry out reactions under an atmosphere of nitrogen. The one on the left would be suitable for a not very sensitive reagent, but in a reaction which may take a long time to go to completion, like this Grignard reaction that we have set up here. Note that we're taking the extra precaution of drying the cylinder nitrogen by passing it through concentrated sulfuric acid. This second bottle is to stop any spray from the acid from passing into our reaction. We use the mechanical stirrer whenever we have solids as well as liquids or solutions involved in our reaction. And we maintain a positive pressure of nitrogen, which is allowed to leak out through the stirrer seal and through this silica gel guard tube without allowing oxygen to enter the reaction. The second diagram shows agitation maintained with a magnetic stirrer, as we see in the setup we have here. Once again, we have a positive pressure of nitrogen entering the apparatus here, passing down through this PTFE tube into the reaction mixture, and escaping from the apparatus through this oil bubbler, which is even more efficient at maintaining an oxygen-free atmosphere than the guard tube. We also here have a pressure equalizing funnel, which allows us to add a reagent without exposing the interior of the apparatus to the air. I've replaced the stopper in the diagram with a rubber septum, which allows me to introduce a further reagent using a steel needle. When the needle is withdrawn, the septum seals itself again. I now want to show you how to transfer a solution of one of these sensitive reagents using nitrogen pressure. I must emphasize, however, that this is only a simulation, and I shall be using only solvent and not reagent in this demonstration. If I were doing a live transfer, I would certainly be doing it in a fume cupboard. I use this double-ended steel catheter. One end is inserted through a septum down below the level of the reagent solution, and the other end through another septum into this measuring cylinder, which we're using as a vessel in which we can measure the amount of solution we require. This septum also has a nitrogen escape leak, again through one of these oil bubblers. I introduce nitrogen through a steel needle and turn up the pressure opening this spring clip. Reagent solution flows into our receiver. You can see the solution being transferred into the measuring cylinder here. When we have the necessary amount of reagent transferred, we can close off the nitrogen, withdraw the needle, and raise the catheter above the level of the solution. We then remove the nitrogen leak and transfer our measured amount of reagent close to our reaction vessel. We now remove the catheter from the reagent bottle and rapidly insert it through the septum into the reaction vessel. Now, using our nitrogen line, after pushing the catheter down to the bottom of our measuring cylinder, we transfer from cylinder to reaction vessel by turning on the nitrogen pressure. If we were using a very sensitive reagent, we might wish to carry out this transfer into our measuring cylinder in the controlled atmosphere of a glove box. Many of the reactions that you encounter in this course require low temperatures. These are needed to generate kinetic products, or to preserve unstable intermediates, or to avoid unwanted side reactions. If we use liquid ammonia as a solvent, we're able to have a temperature of -35 or so, because this is the temperature at which liquid ammonia evaporates. Otherwise, we need to use a cooling bath with a cooling mixture. If we need temperatures between 0 and -20, these are easily generated using a mixture of ice with an inorganic salt. Here we have a salt-ice bath, and you can see that the temperature is well below minus 10 degrees. If we need lower temperatures, for example, minus 70, minus 80, we have to use a reaction coolant of this sort. It is acetone and dry ice, the same that we used for cooling the traps in the oil pump. A temperature between minus 70 and minus 80 is easily achieved here. You can see that the thermometer is reading round about minus 80 degrees. We need to use a spirit thermometer to measure these temperatures because mercury would freeze. For the last sequence, I'm going to show you one of these reactions using sensitive reagents carried out at a low temperature, and we'll need to set this up in the fume cupboard. In this reaction, I shall be adding butyl lithium to a solution of diphenyl acetic acid to generate the dianion. All the apparatus here has been carefully dried in an oven and kept in a desiccator until needed. The solvent we are using is specially dried and redistilled THF, tetrahydrofuran. Because the reaction is only taking a short time, I'm using dry nitrogen from a balloon to maintain the atmosphere of nitrogen within the apparatus. I shall add the butyl lithium in hexane solution through a syringe. I know I need about 5 centimeters cubed. The first persistent appearance of the yellow color indicates that all the monoanion has been formed. And I then need to add just twice as much